Hi, team. Hello? Hello?
Yes, Darshan, we able to hear.
Yeah.
Hey Darshan,
Hi, sir. Yeah.
yes, Mr. Darshan, we were surprised where you went and all. We are actually
Sir,
searching for you on Google.
no, sir. Actually, I was preparing for core demo, like, so that's why it was delayed.
Okay. Darshan, ಎಲ್ಲಿ ಅದಪ್ಪ ಎಲ್ಲಿ ಇದೆಯಪ್ಪ like you were actually searching.
Yes.
Yes,
Can
Mr.
you,
Darshan, you can go on.
yeah, sir, can you enable me to share?
You're unable to share? Okay. Oh. We know the problem. We'll fix it. Okay, try now.
Yes, sir.
Okay. Now no stopping. Go.
Yes.
It's recording. Ravi already has a lot of questions for you, Darshan. That's what he told me. Prepare an Excel sheet. Small. Oh, it's crazy. GPU architectures and Cuda. Oh,
Okay.
Cuda.
Can I start, sir?
Yes, you
Yeah.
can. Yes, sir, you can start, sir.
Yes.
Unless your sir have some objection.
Yes. Yeah, good afternoon to all. Thanks for joining this session. So today I'll be going to present a session on GPU architectures and CUDA. So I'll be covering in depth of the GPU architectures, I mean, starting from Tesla to latest Turing. And then I'll be giving an overview of CUDA, what is CUDA and CUDA programming model. And then at last we'll have a code demo of running in a collab, okay, with the
Okay.
NVCC.
Darshan,
Yes, sir.
when you upload this deck, right, please put SandLogic logo on all the slides, please.
Okay, sir. Yes. Yeah. Yes. Yeah. So yeah, first I'll be covering with the GPU, like vectors, vector processors, and then I'll be moving to the GPUs. So if you see, you can ask like why what is GPU, and what's actually what is CUDA and all. So actually during 2000s and 2000, like 1995 2000, right? So only CPU was handling the both GPU graphics as well as general purpose. Okay, so CPU only was handling the both normal computational tasks, and along with that it was handling the graphics rendering application. So what happened was there was a lot of delay. The performance was not good when the CPUs were handling this graphics processing pipeline. So what happened is Nvidia, Jensen, who was working in AMD. Actually, he found out that why can't we create a processor, separate processor for only graphics rendering, okay, only graphics rendering, and CPU for only computational tasks. So that's where the GPU comes. Okay, he found the Nvidia in 1993, and along with that he found out some the latest the GTX and Tesla Fermi. So from there the GPU architectures evolved. So actually from 1995 2000 to 2005, so only GPUs were only being used for graphics. Were only used for the gaming purpose, but it was not being able. It was not was used for this general. Deep learning, scientific computing in marine, so high performance computing. So what happened was in 2005. So CUDA was developed. So why is CUDA? So what is CUDA? Like CUDA is a programming model, compute unified device architecture. So for using CUDA, you can run all the general purpose computation on NVIDIA GPUs. On NVIDIA GPUs, you can run all the general purpose applications like scientific computing, so I mean supercomputing, high performance computing, deep learning applications using CUDA. So for graphics rendering, you don't need CUDA. For only general purpose, you need CUDA. So that's where from 2005, this GPU, NVIDIA GPUs were also being used for these general purpose applications. So yeah, coming to the parallelism, like parallelism is everywhere. Like in terms of if I can explain, it can be done with the pipelining. It can be done with the vector processors, array processors, multiprocessors, and heterogeneous like CPU with GPU, CPU with FPGA, CPU with VPU. So actually, like it can be done it can be done through these several ways with multi-cores, multi-computers, with the graphics processing unit. Okay, so with this all you can implement you can enable the parallelism, okay, to run your applications. So first I will cover with what is vector processors. So yeah, as I said, in 1990s and 1995, actually these were used for uh, the parallelism, right? So parallelism in the sense like like each registers there were having a register banks. So and these register banks used to store the vectors, and you have the vector like the functional unit which was also vectorized. So if you have a multiple data units like v1, this is v1 and v2. So if you want to compute in parallelly, so this functional unit is also be I mean you has to be also multiple thing, right? So if you have here, so here like if you have a registers like the register banks, so you need multiple functional unit like if you have here. So like the this one is without the multiple uh, functional unit, and the right side here you have this three multi functional unit. So what happened is actually so these are these were before GPUs. Okay, so these vector processors were before the GPUs, like vmix was a one vector processor which was having the eight registers, eight vector registers, and that vector registers and each of the vector register hold the 64 element. Okay, so one if this is a one vector register, so it used to hold the 64 elements. So here only we have five elements. So it used to have a 64 elements, and each of these element used to hold the 64 bits to represent any number. So this element used to have a 64 bit to represent a number. So this was with the vectorized MIPS. So this was all about basic vector processor, like how the parallelism was happening. Like if you see, these are the register banks, and what used to happen is the I mean the functional like if you used to compute like plus or minus, so it was used to happen parallelly, right? So for example here, so here you were doing the serial tasks like A1 B1 they are computed, and after that A2 B2, and after that A3 B3 A4 B4. So like this was I mean this was not a good idea, right? So if you have a register banks, uh, of course it's a vectorized, but you need to have a multiple functional units to have a parallelism. So that's where this multiple functional unit used to process multiple chunks of registers. Okay, so like you are here like A4 B4, and A5 B5, A6 B6, and A8 B8, A9 B9. So like this way the parallelism was involved. And also this we normally we use for loop, right? So any code like of course they will be having a for loop and looping structures. So for that there involves a compiler. So compiler, what compiler need to do is it has to take the for loops, and it has to map the code, it has to generate the code in the sense like it has to run on this parallel vectorized I mean vectorized functional unit. So the actually with the vector processors, there was a evolvement of the compilers as well. So compiler used to take that loops and it used to vectorize the code. Like now we have a advanced compiler for deep learning as well. So the it also does the same actually. So it takes the multiple loops and it converts to the optimized bit file or the executable file, which will be running on the vector processors. Okay, so this was all about vector processor. Yeah, so if you see the Moore's law, right? So Moore's law, what's Moore's law? Actually, Moore's law gave a one law. So Moore's law told that Moore, so he was a founder of Intel, Gordon Moore. What he said, the number of transistors in a chip will be doubling with every 18 months or maybe 2 years. So for every 2 years, the number of transistors in a
I
chip
think he said every
will be
year.
doubled.
He said every year,
Yeah,
not 2 years.
no sir, like it's a 18 months, it's a 18 months sir, but everybody like instead of remembering 18, like everybody will say 2 years, like. So yeah, so yes, like now this Moore's law changed to the Jensen's law, like Huang's law, the Nvidia's founder, Jensen Huang. So this Moore's law is now changed to Huang's law. So what Huang suggests is the performance of the GPUs will be doubling every 2 years, right? The performance of the GPUs will be doubled every 2 years. So this Moore law has been changed now to the Huang's law, right? So what like Moore's law is not it's not there now, like it's already over. Why? Because the single threaded performance, it's flattening now. The single threaded performance is flattening and the frequency is also becoming flattening, like but the number of transistors is growing for in the chip. But what's happening is the performance of the single thread, so it's normal, like we can't increase, it's becoming flattened. So because of this, like we need to come up with a parallelism. So that's where the GPU comes. So GPU, yeah, so this is the basic architecture of GPU. So this was a G4 Tesla GPU. So this was a this was came up in 2006. So yeah, so this was a basic GPU. So like it has a hierarchy. We have a TPCs, texture or thread processing clusters, and it has a streaming multiprocessors, and in the streaming multiprocessor we have a scalar processors. So this is the hierarchy actually. So if we see uh, these upper blocks like host interface, input assembler, clipper setup, so these are mainly used for graphics. So this above are mainly used for graphics, and also like graphics also need this TPCs and all, but for general purpose we need only this these blocks like TPCs. Okay, so and the memory, right? ROP, L2 cache, L1 cache, DRAM. So if we see the hierarchy of this Tesla GPU, so this was a main architecture, first architecture. Like we have a different now, like we have Volta, Pascal, Turing, and some Maxwell. So this Tesla was a first GPU architecture by Nvidia. So in the Tesla, so we have texture processing clusters, and in that we have a streaming multiprocessor. So if we see the streaming multiprocessor broadly, we have eight scalar processors and SFUs, special functioning unit. So here normal integer operations and floating point operation will be performed in these SPs, right? In the SFUs, all the transcendental operations like logarithm, sine, cosine, square root operations will be performed. So yeah, but the thing is like SPs are independent with the SFU. So if you're running any integer operations, like you can't. These operations running on SPs will not be dependent on SFUs. So that was a one thing. Yeah. So this is a basic architecture of the GPU, like Tesla GPU. The Tesla is architecture, and GeForce 8800 is a name of the GPU. Name of the GPU. Like we have a 1080 Ti, 1080 GeForce RTX. So these are the names, but the architecture name is different from the name of the GPU. So this is name of the GPU, but the architecture name is like we are going to discuss about that. Like here, if you see Tesla, Fermi, Kepler, Maxwell, Pascal. So these are the name of the architecture. So latest now we have Ampere. Okay, so now we have ampere, and in Kepler, like in Jetson Nano, we have this Kepler. Okay, so in some other like in VM, some like Maxwell we have. So like if you see, GPU earlier figure depicts the GPU with the array of 128 scalar processors. Okay, 16 streaming multiprocessor. So this GPU had a 16 streaming multiprocessor, right? So 16 streaming multiprocessor, 16 in the sense like 8 TPCs we had, 8 TPCs, 16 total, 16 SMs like streaming multiprocessor. And in each streaming multiprocessor we had a 8 scalar processor. So 16 into 8, 128 scalar processor we had in the GeForce 8800 Tesla GPU. Yes, so yeah, each SM has a 8 SPs. This is scalar processor, and the two SMs together are arranged as a independent processing units called texture processing clusters. So texture or thread processing cluster. So this is the texture processing clusters. So what happens is so in this SM, in this individual SM, uh, we have a we have a shared memory. So if any thread running on like thread so like we are if we are running the process, so at the low level thread will be running the process. Okay, so what happens is like the threads will be running on these scalar processors, and these three like assume like if this the thread running on the first block will want to communicate with the thread running on the last block. So like it communicates with a shared memory here. Okay, these communications happens with a shared memory. But if the thread running in one SM has to communicate with the other SM, so it used to share the shared memory becomes the DRAM there. If the thread in one SM has to communicate with a thread in another SM, DRAM becomes the shared memory. Okay, but in between the in SM, like between it has a shared memory, separate shared memory will be there in communicating uh, with the threads which are running on these SPs. So two SMs, yeah. So this is what. So if you see the GPU architectures, right? So yeah. So first was Tesla, and next is Fermi, Kepler, Maxwell. So now we have a latest. Like this year, Ampere was released in NVIDIA. After NVIDIA GTC, like in the March, in the March GTC in the so this Ampere was released. Okay, so as I said, for this session will be mainly covering for general purpose GPU. It will not be focusing on the graphics part. So I have one slide which is a basic graphics rendering pipeline. So rest all will be focusing on deep learning or other general purpose applications. Okay, so yeah, so each TPC has two SMs. So this I covered, and eight scalar processors were there in each SMs, and two special functioning unit whether in each SM, right? The Yeah, so this empty issue, what the empty issue block, so what empty issue will do is it issues the instructions on to these scalar processors, right? So that will be done by the empty issue. And yeah, there will be 16 kilobytes of shared memory will be there in SM, and each SP core contains a scalar multiply add unit. Okay, giving 8 multiply add units in the SM. Okay, so this SPs has MAD, so multiply and addition. So this so we have 8 SP. So each comprising of the uh, one multiply and addition block, so unit. So comprising of this SM will have total 8 multiply and addition unit. So the SM uses its two SFUs for units for transcendental functions. Like we have a as I said, like we have log, square root, sine, cos. So those functions will be performed on the two SFUs. Okay. So if you see, so this was a basic, I mean, the graphics rendering pipeline, which presently is happening. Like if you are running any if you're running a, I mean, gaming on gaming applications on GPUs, like this is actually the pipeline. Like what happens is we have a programs called shader programs. So those shader programs actually gives the appearance for gaming on the GPU on the screen. So those shader programs like are heavy compute intensive. So like actually these blocks, these like vertex shader, geometry shader, so these are mainly used for different like this will be used for drawing the triangle, and this will be used for drawing the points, and some, and this will be some other shader will be drawing some polygons or something. So these are mainly used for actually these are all called uh, the shader. Like shader means the program, like uh, it's a program, I mean, to give the appearance on the GPU, right? So on the screen. Okay, so that those will be computed on the GPUs. So using these above blocks like host, yeah, like clipboard setup, raster, and compute work distribution, like so vertex work distribution. So this the GPU uses these blocks to run the graphics rendering applications. Yeah. So next we'll go more to the Fermi architecture. So Fermi was a next evolved architecture compared to the Tesla. So like in Fermi we had a 16 SMs. Like we'll go with the detail here. So it had a 16 streaming multiprocessor with a total of 512 CUDA cores. Okay. So each SM had a 32 SPs. Like SP in the sense that these are the CUDA cores. So each SM has 32 CUDA cores, and 32,768 registers were there. Okay, in the total this GPU, and one thread has a maximum limit of 64 registers. Okay, so if you see actually there is a warp. So warp is a collection of 32 threads. So 32 threads, like while we are running a CUDA programs, will launch threads like in the blocks. So in the warp, so that warp has a 32 bit. Like it depends on the different architectures. So for me, like it's a 32 bit for a 32 threads comprising for a the warp. But in other like ampere, like we can see 64 uh, threads comprising for a warp. So like 64 register into 32 threads. Okay, so this is a warp. So I mean warp has a 32 threads. Okay, 32 into 64 is those number of registers are there, like 64 into 32 will be 32,768. Okay, because like one thread will be can access 64 registers maximum. Okay, so yeah, 64 into 32 so will be 32,768. So warp can access 32,768 registers. Okay, so each SM has four SFUs, and like each SP has one FP, one integer ALU. Like if you see, so this has four SFUs. Like earlier we had two SFUs in one SM, but it has a four SFUs. Like this way the evolution happens. So uh, like here we have a 32 SPs, like CUDA cores. Okay, each CUDA core will be having FP unit and intake. Okay, so yeah, so this is the inside of the core SPs. Okay, if you see each SM had 16 load store unit. Like so this is responsible for, these are responsible for loading the data from DRAM and giving it to the cache. So like this way this will do the functions. Okay, so each lane, in the sense like each this load and store unit has 2048 registers. Okay, and each SM has four SFUs. Okay, so these four SFUs are there, and each SP has one FP and one integer ALU, one FP floating point unit and one integer unit. Okay, so yeah, so this is a basic SM of Fermi GPU. Okay, so like you can see the evolution. Like earlier we had a eight SPs in the one SM, but we here we have a 32 SPs in one SM. Also we have four SFUs in one SM compared to the two SFUs in earlier. So this is a memory hierarchy. So if you see for a thread, so shared memory is nearer when compared to the L2 and DRAM. Okay, so DRAM is much faster and the access speed of DRAM is more compared to the L1 cache or the shared memory. Okay, and also if you see the size of the L2 cache is more compared to the shared memory, and the size of the DRAM is more than the L2 cache. Okay, so this is a memory hierarchy for the Fermi GPU. Okay, so yeah, I'll move on to the deep learning. Okay, so deep learning with the GPU. Okay, so that will be interesting bit. Okay, yeah, so I gave, till now I gave a brief I mean the introduction with the SM, like, so these are basically these SMs, SPs are basically in Ampere also, in latest also. The architecture remains same. Like the architecture remains same. Like we have a register, warp scheduler. So these all remain same. But only thing is the flops, memory bandwidth. So those only will be evolved, and the number of cores will be evolved. Okay. So that's the only difference if we compare with the latest to the latest with the earlier GPUs. Okay. So if we see GPUs, we
Darshan, I
can,
have a question.
yeah. Please ask.
Yeah, DRAM and L2 cache,
Yeah.
which is more having the size less size as DRAM or
Okay.
L2 cache, and which is used first?
Yeah.
Like
Yes.
we have used in a
Okay.
hierarchical way.
Okay.
So
So
which
yeah,
one was
DRAM.
used first?
Yeah. So I can say like L2 cache and DRAM are outside of SM. Okay. So L2 cache and DRAM are outside of SM. So if one thread from first SM and second thread from second SM has to communicate, so it has to communicate through DRAM and L2 cache. Okay, but these shared memory and L1 cache are inside the SM. Okay, so are inside the streaming multiprocessor. If you can see this, you have L1 cache and shared memory, right? So this is inside the SM. So this is the SM. Okay, so this is inside the SM, but DRAM and L2 cache are outside the SM. Okay, yeah, so these are outside the
Okay.
SM, but DRAM is more in size of L2 cache. DRAM is more size of L2 cache, but DRAM access, the access speed of DRAM is very less. Okay, but because it is far from the core, like, so if here the thread will be executing, but the DRAM is outside somewhere like here. So the communication will be like this thread running here wants to communicate, like there will be a delay because DRAM is more fast. Okay, so that's where like now we have APIs, like now we have a compiler. So what they are like using the compilers, what compilers with the evolution of compiler technology, like I mean the thread will get the communication between the SMs SMs, the communication of the thread between the SMs will be lowered with the compiler technology. So that's a one thing. Yeah. So if we see GPUs, we can find everywhere. Like we have in mobile GPUs, like we have ARM, Mali, Adreno GPUs, right? So Adreno is from Qualcomm. So these are used for both graphics and also the compute tasks. Like we have a face unlock, right? So that application needs a more compute intensive task. So that will be run on these ARM GPUs and Mali. Okay, so yeah, then we can see the GPUs in embedded space also. Like we have a Zetson Nano. So now we are using it. So Zetson Nano TX1 AGX. So targeting. So these are mainly targeted for deep learning model deployment. Okay, so these are not meant for any IoT, like Raspberry Pi kind. So these are mainly used for deep learning. Okay, so and also we have a NVIDIA drive. Maybe like some of them are knowing this one. Like it's a NVIDIA drive is a platform for self-driving cars, like autonomous. Okay, so this is autonomous. So autonomous cars, ADAS applications, right? So they have the platform called NVIDIA drive. Okay, so there also we can found the GPUs. So what I meant is like GPUs can't be. I mean we can't. there are we can see GPUs everywhere. It's not like we are seeing only in cloud training, like in the laptops, right? So we can found everywhere. Okay. So if we see the NVIDIA Zetson series, right? So this is a architecture of TX2. So we have a Kepler GPU here. So Kepler GPU has a 192 cores, and we have a four CPU. Okay, so yeah, so which has a instruction cache and data cache. Okay, so yeah, so this is a basic architecture of NVIDIA TX1 embedded GPU. Okay, so this is, so one thing I would say is one point I want to say is, wherever the GPU is there, CPU has to be there. Okay, so wherever GPU is there, wherever, you can see everywhere, GPU, with GPU, CPU has to be there. Okay, GPU is always married with CPU. Why? Because CPU actually will be like GPU acts as a slave, and CPU acts as a master. So CPU will send the data, and it shares the the instruction, scheduling, all the data orchestration and all will be uh, handled by the CPU, and rest of the functions, high computation task, will be run on a GPUs. Okay, so and another point is the core in the single core in the GPU is not stronger than the single core of a CPU. The like If you see, in GPUs we have a 1,000, 2,000, 3,000 number of cores, but in GPUs, in the CPUs, we have only 64, 128, 8 cores, 4 cores. Okay, so but if you compare with one core of CPU and one core of GPU, the CPU core is much more stronger than a GPU core. That's a one point I would like to say. So yeah, so this is the basic architecture of the NVIDIA TX1. Yeah, and then yeah, so if you want to go fast, you use multiple processors. Okay, and if you want to go efficient and fast, you use GPUs. Okay, and if you want to be efficient and go really fast, you use multiple GPUs. So this is the thing what I want to say. Like, if you want to go fast, you use multiple CPUs. Okay, so if you want to be efficient and fast, use GPUs. Fast, efficient, and go really fast, use multiple GPUs. Okay, so yeah, if you see GPUs for training, right? So NVIDIA Pascal, so this was released in 2015. So it had only 10 or 20, 10 to 20 teraflops. Okay, this is teraflops, means this is the flops means the floating point operations per second. So if you want to benchmark one GPU to one GPU, so there are three main part. One is flops, and another is memory bandwidth, like HBM, DDR, DDR4, DDR3, HBM1, HBM2. So this is the second part, and the third part is the inter GPU communication, like PCIe, NVLink. So these three point are the main part to benchmark, to compare one GPU with another GPU. If you see, so this is a Pascal. So this was not stronger. Uh, Okay, so this was not stronger GPU. In 2015, they launched this one. NVIDIA launched this one. If you see the Volta, so this Volta was specifically meant for deep learning. Okay, in 2016, 2015 to 2016, deep learning evolved like anything, it evolved more. Okay, so that's why NVIDIA launched this Volta, NVIDIA Volta. So this is specifically meant for deep learning. Okay, I'll tell why it meant for specifically for deep learning, because it had a tensor core, which where we can run a mixed precision, like we can run a 16-bit FP32 or FP16. So that's why it's specifically meant for deep learning. Okay, if you compare, the teraflops here were 20 teraflops. If you see, 120 teraflops were there. Okay, and if you see the memory bandwidth, it was around 900 Gbps. So here I'm comparing Volta and Pascal GPU. Okay, Volta is advanced than Pascal. Okay, so it has 750 Gbps, so it has 900 Gbps, but the power consumption is almost same. Okay, so this is same for uh, I mean uh, Pascal, Volta, Pascal, Volta, Ampere, Turing. So this is same the power consumption, the 300 watts. Okay, and the transistor technology, like it used 16 nanometer technology and it used 12 nanometer technology. And as I said, right, so between the inter GPU communication, so it has around 160 Gbps, but here it is around 300 Gbps. So this is how it worked actually. Like Nvidia actually this was a major change, Nvidia coming to the deep learning. Okay, so yeah, so this is a comparison between Nvidia Pascal and Nvidia Volta. Okay, so yeah, as I said, right, so what's the difference, like why it's specifically meant for deep learning. Okay, so yeah, if you see any application, right, it is running in double precision or single precision, like FP32 mode or FP16 mode. Yes, like if you have a number, right, so all the, like if you all the numbers, like all the code you write will be converted to the bits. Okay, so each number, if you see, each number is represented in 32 bit, 64 bit. Okay, and if you like those 64 bits and 32 bits computation is huge. Okay, so those are floating points. Okay, and if you convert to FP16 or int8, the computation will be fast and the memory requirement will not be that much. Okay, if you compare with FP16, int8, with the FP64, FP32. Okay, so yeah, what's new in Volta, right? So Volta had a tensor core. Okay, like we had a core right here, we had a core, right, CUDA core. So in the Fermi, in Volta we had a tensor core, like so this was separate tensor core which was specifically meant for deep learning. Okay, so yeah, if you see what is I mean what's exactly happening in tensor core there is a mixed precision. Okay, so if you see like FP16 and FP16, like this is a matrix. Okay, this is matrix multiplication. Okay, the multiplication is happening with FP16. Okay, the multiplication is happening with FP16 after multiplying. Okay, 16 into 16, like it's 32. Okay, 16 into 16 is 32. Okay, like this is 32. It's a mixed precision, right? So below, like if you see, like if the tensor multiplications will be like in a huge, like there are huge multiplications, like matrix multiplication, right? So if you are running with FP32 mode, then there'll be huge the computations and there'll be a memory requirement of it's very huge for FP32. So this is the main functionality of the tensor core. Like I'll just give more detail about that. Like if you see, so you have two numbers. Okay, so if you want to multiply, you convert to the FP16. Okay, FP16. So this is a basic multiplication and accumulate operation. I'm giving an example. So FP16 will be coming, the resulting will be FP32. Okay, and FP32 you need to add. Okay, so it will be the same. FP32 will be given to the FP16. Okay, so if you are again multiplying and with the FP32, you again convert it to the FP16. Okay, you convert to the FP16 again if you want to multiply like this. Okay, so this is what the speciality of the mixed precision. Okay, yeah, so with the deep learning training, right, so I'll just brief, like you have a gradient descent, right, w minus uh, learning rate into gradient. Okay, so if you see w goes here, like the w, like this is converted to the FP16. Okay, so this is converted to the FP16. Okay, and then like this while we are doing a uh, learning rate into gradient, right, so that has to be with the uh, FP uh, 32. Okay, so like in order to like so that is that minus, right, so minus learning rate into gradient, it's a memory like, not memory, like it's a accuracy oriented. Okay, so if you are computing with FP16 there also, like you are losing accuracy. Okay, that's where you need to compute with the uh, FP32, like while you are doing minus. Okay, so that was one intuition with a mixed precision. Okay, so like yeah, you can use, like while you are training you can use this mixed precision. So like if you're like if it if it's taking 6 or 7 days to, training, like it will be reduced to the 3 4 days for training if you are using mixed precision. Okay, so that the GPU which you are running has to be only Volta, not the earlier version. So yeah, this is the SM of the Volta. If you see, so this is really huge. Okay, when you compare to the Fermi, so like you have a, FP64, 8 FP64 cores, and 16 int in 32 cores, and 16 in FP32 cores, and here we have a tensor core. So in this course, you run a deep learning training, okay, deep learning applications. Okay, so so this is a streaming multiprocessor of the Volta architecture. Okay, yeah. So if you see the comparison, right? So if you see the with respect to the Pascal and Volta, right? So you have a, like, there is a huge I mean huge boost in the performance when you compare to the Pascal with the Volta, right? So this is the performance comparison. Okay, so if we see the, the evolution, right? So we have a Kepler, we have a Maxwell, we have a Pascal, we have Volta. If you see, the clock speed is like it's also increasing, like, so earlier for Kepler we had 810 megahertz, for Tesla we had 1.4 gigahertz. So you see like how it's increased. And if you see the flops which is increased, okay, so 5.04 to the 15 teraflops. Okay, and the tensor flops, like earlier in this one, like there were no tensor flops, okay, tensor core. Okay, here it's a 120 teraflops. Okay, and the memory interface, the bandwidth, okay, so like it's really huge, right? So here we are using a GDDR4, here we are using a HBM2. Okay, so HBM2 is a high bandwidth memory, so it's very advanced than the DDR5 or GDDR. Yeah, so yeah, and then the TDP, yeah, the power consumption, as I said, it's almost same with with the GPUs. Like it's becoming more, because like you have a more number of cores, okay, in Volta. Okay, so that's why like the power consumption is more, the heat generated is more. Okay, so yeah, that's one advantage. If you see the GPU, the it takes a lot of power, and the heating, like there'll be a more heat. Okay, if you compare to the TPU, so TPU uh, will not consume more power than GPU. Okay, if you see the transistors in Kepler, we had a 7.1 billion, but in Volta we had 21.1 billion number of transistors. Okay, and yeah, the GPU size, like the chip size. Okay, so this is a chip size, like it's becoming more also. The card, like you have a card, right? GPU card. So the size of the card is for Volta, it's more. Okay, and the manufacturing is like for Kepler it was 28 nanometer, and for Tesla for Volta it's around 12 nanometer FinFET. Okay, so yeah, so till now we discussed about the GPU architectures, like in detail, like about SMSPs with Tesla, Fermi, and Volta, Pascal. So now we'll be going with the CUDA, so CUDA programming. Okay, so yeah, like in CUDA, what is CUDA? You can ask me. So CUDA is it's a programming model. Okay, everyone thinks it's a programming language like C, C++. It's not that. So CUDA is a programming model where you can use it in C, C++, Python. Okay, with including the header files. Okay, and runtime. So if you see, CUDA is an extension of C programming language with special constructs. Okay, so it has a different functions uh, supporting for parallel programming. Okay, so for GPU you have CUDA, but for CPU you have OpenMP MPI for parallel programming model. Okay, and for AMD you have Stream. Okay, and for other FPGA and all you have OpenCL and other programming model. Okay. So this is the CUDA is basically the parallel programming model for NVIDIA GPUs, only for NVIDIA GPUs. Okay. If you see CUDA programming CUDA programmer perspective, so CPU is a host. Okay, as I said, now for whenever the GPU is there, wherever the GPU is there, CPU has to be there. So for CUDA perspective, uh, so GPU is a host, CPU. So sorry, CPU is a host, GPU is a device. Okay? GPU is a device, CPU is a host. So CPU actually will dispatch the parallel jobs on the GPUs. Okay? So GPUs will dispatch the jobs to run on a GPUs parallelly. Okay? So if you see the host code is there for a host device. I mean the host, the CPU, and the device code is there for a GPU. And any C programming, normal C programming. If you see normal C programming, it's a valid host code, right? It's a host code. Okay. In general, CUDA programs like host plus device code cannot be compiled by the standard C compiler. Yes, of course, because if you see the CUDA programs are compiled using the NVCC compiler. Okay, what it does is, what NVCC does is, so in the CUDA file, right, the the script which where you written the CUDA program, during the compilation, what NVCC does is, so there in that script you have a CPU code also, GPU code also, right? So for GPU code, the CUDA, the NVCC will convert the CUDA program, the GPU code to the PTX code, like the assembly code we have for CPU. The PTX code is for GPU. Okay, so that NVCC will convert the GPU code into uh, the PTX code. Okay, that PTX code will be again converted to the bit file. Okay, based on the GPU where you are running. Uh, so it has other compiler which will be taken care of converting the PTX to the bit file for running on the different GPUs. Okay. So yeah, that's one part for for the GPU side. For CPU side, what NVCC does is, NVCC calls the already CPU compilers, like you have GCC and other compilers, right, for C programming. So it invokes that compiler for compiling the normal host code. Okay, so this is the basic operation of the NVCC compiler. Okay, so if you see the execution flow, you have a CPU serial code. So what I mean, so first you will execute the CPU code, and then CPU will issue the jobs to run on a GPU. Okay, so that function is called a CUDA kernel. Okay, so that function is the kernel. Okay, after that, I mean, after operating on the function, then it will give the result back to the CPU. Okay, and then it will again run some of the serial functions which will be running on the CPU, and then again you will be having some other functions. Okay, so if you see, like if you download the CUDA, right, CUDA toolkit, there you will get all the CUDA kernels, CUDA runtime, NVCC compilers, all you will get when you download the CUDA. But for yeah, but actually below these compilers, there's also driver. So what's a function of driver is, I mean, a driver will take care of all the data flow. Okay, like I mean, like the compiler will generate the bit file, but driver will take care of way to, I mean, how the data flow, like from cache to SPs, and from SPs to again the L1 cache, from L1 cache to DRAM. So like that way the data flow is there, right? So that will be handled by the NVIDIA driver. Okay, so that's the functionality of driver. So this is basically the execution flow of the CUDA program. So if you
Darshan,
see, this is, yes
Darshan,
sir, yes sir,
sorry to disturb you. So there is a time check. We have 5 minutes.
yeah, yes sir,
How long
yes
it will
yeah
take?
I yes sir,
Just
I'll try to complete, yeah, yes sir.
okay.
So yeah, if you see this is a basic CPU code. So this is a basic vector addition code, which is a CPU code. Okay, so normally the execution start from main function, and so you are defining the pointers here, and also like you are dynamically allocating the memory, and you are passing the pointers to the these variables. Okay, and then you are calling the vector add function. Okay, so this will be running the I mean the this function will be computing this part. Okay, so this is basic, this is basic CPU code, right? If you compare that to the GPU code, so it's all same, but you have to include the files cuda.h and cuda runtime.h. Okay, and what changes is so this you need to mention, explicitly mention this keyword global. So when the compiler checks which part has to be gone to the GPU, so if it sees, right, so if it sees this keyword, so below this function will be there, right? So this function will be executed on the GPU. So this is the CUDA code. So this is the GPU, like so this is a CUDA kernel. Okay, so this is a CUDA kernel which will be executed on the GPU part. Okay, so these are all like, so if you see, right, so these are all the host program, so which will be running on the CPU part, but this part will be running on the GPU part. Okay, yeah, so this is a main difference. Okay, so it's not much difference, like yeah, if you see here, you are you have a the pointers here which are defined, and so what you do is, like, while you are allocating the memory on the device, right, so you need to allocate the memory on the GPUs. Okay, so you need to allocate the memory on the GPUs uh, for this variables, like you are computing right here, so A B, so you need to allocate the memory for this. So that's what you are doing here. So CUDA malloc. Okay, so yeah, so it's the CUDA malloc. So after so the result of the CUDA malloc will be, I mean, like it will I mean, it will return some of the signatures, right? So like if it's error, then this code will be executed, and it will throw like the fail to allocate CUDA device vector. Okay, so like this way it will throw the error. Okay, if it's the signature is the error. Okay, and the same for the other one, the other variable, like you are allocating the memory for B here. So this is the DB, means the device side. You are allocating the memory for device, in the device, the GPU. Okay, so the same thing here. Okay, and for C, so this is the results. And so yeah, once you allocate the memory in the GPU, so you need to pass the data from CPU to GPU, right? So these functions, this function will do that. Okay, so this function call, what will do is you have a device and host array. So device array and host array. So what we'll do is so this function will copy the data from CPU to the GPU. Okay, so you need to mention the size. Okay, how much size you want to transfer. Okay, so this is same. Okay, so this is B array and this is A array. So you are transferring from CPU to the GPU. So next thing is the launching part. I mean, launching means the you are running. Okay, running this kernel. You need to call, right. So you need to call this kernel. So so this is a line which is calling the CUDA kernel, the kernel. Okay, yeah, so vector add is the name of the kernel, and you are passing the blocks per grid and the threads per block with the this data. Okay, and with n is like the length. Okay, length of the array. So this is the basic program, like here. So this is the main, like you can ask me like what is blocks per thread, and I mean blocks per grid and threads per block. So I have one slide. So if by that you will get to know what this means. Okay, so while you are launching, right, so you need to launch in thousands of threads. Okay, so those thousands of threads uh, will be launched in grid. Okay, so in grid you have a blocks. Okay, in blocks you have again the threads. Okay, so in grid you have blocks, and in blocks you have threads. Like if you see here, here, right, so grid you have a blocks. Okay, and in block you have a in block you have this. Okay, threads. Okay, so this is the basic CUDA I mean the functions. Okay, and if you see here, right, so after the computation, so the results will be in GPU. So those results had to be brought to the CPU again. So that's where you have these functions. Okay, so CUDA mem copy. All right, so you have CUDA mem copy. So the device, the results from D will be converted to the host device. From the result from device will be transferred to the host. Okay, with the CUDA mem copy device to host here. So while you are transferring from host to a device, it was like host to device, and from here we have a device to host. Okay, so device to host. Okay, so and after that you will free uh, the mem- the memories, okay, which you have allocated in the device. Okay, and you will test it whether the computed thing is correct or not. So this is basically the CUDA, the basic CUDA program. And if you see, the CPU will transfer the data from CPU to the GPU, and GPU will do the operation, and so result will be in GPU, and GPU will transfer the result to the CPU with the function. So these are some observations, like CUDA malloc is a uh, so for CPU, for dynamic allocation of memory, you used only malloc. Okay, so for GPU, in GPU you need to use a CUDA malloc if you want to allocate the memory dynamically. Okay, and this CUDA mem copy here, this one, so this is from host to device, right? So this is copying the this eh, this data to the data from host to the device. Okay, with the size of this value. Okay, you need to specify how much size you want to transfer, and then this is same. Okay, so this is from device to host. So previously it was host to device, and it is device to host. Okay, and after that, after computing, you need to free the memory in the GPU. So from this function, you will free the memory. So this is free the GPU global memory. Okay, so yeah, so this is the vector add. So here from this you will be launching the kernel. Yeah, so you'll be passing the parameters as grids, the blocks per grid, and the threads per block. Okay, so you'll be passing, and you'll be passing this for computation. Okay, so if you see, so this is the CUDA kernel. Okay, you have vector add, and so yeah, this is for calculating the ID for the thread. Okay, so you have so many threads right here. So many threads are there. So you need to give the ID for each thread. Okay, so this is 0, 0, 0 of block 1, 1. So that's from that, like from this calculation, you'll get the thread will be given a ID, and that like if the ID is 1, right? So if the ID is 1, that the first index of the array will be it will take the first it will take care of the first index of the array. So, and like second id second index. So like this way, it will take care of the all the elements, and it will compute in parallel. Okay, so this is the basic grids and blocks. So you have in grids you have a 6 blocks, and in blocks, in each block you have a 12 threads. Okay, so this is the function. Yeah, so if you see, right, so device yeah, so this function is called, executed on the device, and called in the device only. But this global, right, so as we had seen, right, so this is this one, this is executed on the GPU, called from the CPU. Okay, so this, if this keyword is there, so after that function, after that keyword, any function is there, that function will be executed on the CPU, and called from the CPU itself. Yeah, so actually I said I said about the kernel, right? So in deep learning, like so every kernel, in the kernel, right, so they used this kind of optimization techniques. Okay, like memory access coalescing, optimizing, reduction kernels, kernel fusion. So
Darshan?
thread, yeah, it's done, sir. Like it's only one.
Okay. No, see,
uh,
this is very interesting. I'm
yeah,
sure if there are more, if there is some more topic now, next week you can still
yes, sir.
cover. You can take 10 more, 10, 15 minutes. And
Yeah,
coding.
yeah.
How many more slides you have?
I mean, I think no, three slides. Yes. Okay.
3 slides. 3 slides. Okay, then finish. Yeah, let's finish.
Yeah, yeah, yes. So yeah, so these are the optimizations techniques, right? So I'll cover kernel fusion first, okay? For kernel fusion only for this session. Okay, so if you like if you have a uh, like two this operation, right, ax plus y, okay, so you are defining here tf dot multiply a comma x, okay, so you are so this is a operation in the tensorflow and tf dot add, okay, but in C++, like in CUDA C++, CUDA C code, like how it will be mapped is tf dot multiply is here, right? So this will be mapped to this one, this kernel, okay, and this will be mapped to the this one. Okay, so you have two kernels here, okay. So in kernel fusion, what happens is these two kernels are fused to the one kernel, okay. So these two multiply and add will be fused to the one kernel here, fuse multiply add. So yeah, so here you are avoiding the memory overhead, right? So if you are launching this kernel, uh, like there is a memory overhead. So if you are launching two kernels, okay, but if you are launching only one kernel, there is less overhead and there will be a more speed up. So that's one kind of optimization. And actually there are more many more programming parallel programming model. So here if you can see OpenMP, MPI, OpenCL, one API, CUDA. Okay, so yeah, so you can look for, okay, if you want to run parallelly, you can use these two on CPUs, okay, and if you have a FPGA, you can use OpenCL and also one API. So yeah, that's all from my side. So if you like, I created one this thing. So the you can execute that one. I'll also provide the text file, the data file, so you can execute this one. Yeah, I think yeah, I took some 10 minutes more. Yeah, it's fine.
That's okay. Yeah, I think we started a bit late. So
Yeah. So if you have any questions, I can take it up. Or...
okay, cool then. So yeah, thanks Darshan. I think thanks a lot, Darshan. This is very
Yeah. Thanks.
informative. I learned a lot. I got to know a lot of things, and it was very detailed. I'm sure you might have spent a lot of effort on this. It was really good.
Thank you,
Thank you.
sir. Thank you, sir.
Thank you
Yeah.
very much.
Thanks for.
Thank you very much, Darshan. Okay, others, any questions before we wind up?